Welcome, engineers, to a crucial discussion on building resilient systems. In today's interconnected world, data flows constantly, and with it, the inevitable reality of imperfect messages. We're diving deep into error handling and poison pills in distributed systems, a topic that can make or break the reliability of your applications. By the end of this lesson, you won't just understand these concepts theoretically, you'll have a practical toolkit to design systems that gracefully manage the unexpected. Specifically, you will be able to implement robust error handling patterns for critical data ingestion. You'll also learn to design and implement dead letter queue systems for effective poison pill recovery. Furthermore, we'll explore how to apply intelligent skip strategies for non-critical deserialization failures, ensuring your services remain operational even when some data is malformed. Finally, you'll understand the paramount importance of real-time monitoring for tracking errors and measuring recovery metrics, giving you visibility and control over your system's health. This knowledge is not just academic, it's essential for building production-grade, fault-tolerant platforms. Let's kick things off by understanding the core problem. What happens when messages go wrong in a highly scalable system? Imagine a large social network processing millions of posts every second. In such environments, corrupt data arrives constantly. A malformed JSON, an invalid encoding character, or even a missing required field can slip through. This brings us to the infamous poison pill problem. A poison pill is a message that, due to its malformation, repeatedly causes processing failures. It gets requeued, retried, and fails again, effectively blocking an entire consumer group and halting all subsequent processing. The real-world impact of this can be severe. Consider a major streaming service that faced an incident where a single malformed video metadata message caused their recommendation engine to stop processing for millions of users. The poison pill exhausted resources, leading to a significant outage. This isn't just an edge case, it's a critical challenge in distributed systems that demands robust solutions to maintain service availability and performance. So how do we categorize these poison pills and what do we do about them? Deserialization errors typically fall into a few key categories. We often see schema mismatches, where a message doesn't conform to the expected structure. Then there are data type errors, like receiving a string when a number was anticipated. Encoding issues, such as invalid UTF-8 characters, are also common alongside missing fields, where required properties are simply absent from the payload. Not all errors are fatal, though. A malformed emoji in one social media post shouldn't halt the processing of millions of others. This is where smart skip strategies come into play. For non-critical formatting issues, we can skip and log the message, allowing the system to continue processing. For temporary network glitches or transient parsing errors, a retry with backoff strategy is effective. But for truly structural problems that require human intervention, we route the message to a dead letter queue, or DLQ, for later inspection and recovery. This tiered approach ensures resilience without overreacting to every minor anomaly. Building truly resilient systems requires a multi-layered defense. Our error handling architecture operates at 3 distinct levels to catch issues as early as possible. First, at the consumer level, we catch immediate deserialization exceptions right as the message is ingested. This prevents malformed data from even reaching our business logic. Next, at the processor level, we validate business logic constraints. This is where we check if the data makes sense in the context of our application, even if it's syntactically correct. Finally, at the storage level, we handle persistence failures gracefully, ensuring that even if our database or storage layer has issues, the message is not lost and can be retried or routed appropriately. Understanding the control and data flow is key. A normal flow sees a message go from received to parsing, then validated, processed, and finally committed. An error flow, however, diverts at the first exception, where the message is categorized, then routed for skipping, retrying, or sending to a DLQ, and ultimately monitored. This structured approach ensures that every message, whether perfect or problematic, is handled intentionally and effectively. We've covered a lot of ground today, and by now you should feel equipped to tackle error handling in your own distributed systems. We started by understanding the critical nature of robust error handling patterns for data ingestion, moving beyond simple try-catch blocks to more strategic approaches. You're now familiar with how to design and implement dead-letter queue systems, a vital component for recovering from those stubborn poison pills that demand manual intervention. We also explored the nuances of applying intelligent skip strategies for non-critical failures, ensuring that minor issues don't cascade into major outages. And finally, we highlighted the indispensable role of real-time monitoring in providing the visibility needed to track errors and measure the effectiveness of your recovery mechanisms. This knowledge is not just academic, it's essential for building production-grade, fault-tolerant platforms. As a final thought, consider this. What are 3 specific scenarios in your current or a past project where a poison pill could have caused or did cause significant issues, and how would you apply these strategies to mitigate them now? Think about it, and you'll see the immediate relevance of today's lesson.